Hello viewers, welcome to one more series on mathematics for class 12. Today we are going to do a very interesting and easy and of course scoring topic. We are going to introduce you to the concept of linear programming. Let us first understand what linear programming is. The linear programming is defined to be a process where we take various linear inequalities relating to some situation and then find the best value obtainable under those conditions. Historically, linear programming is credited to the French mathematician Fourier, who formulated the linear programming problem, and then further Kantrovich, a Russian mathematician, developed the problem mainly for the purpose of improving economic planning in Russia. And then World War II gave rise to the need for urgent use of resources to the utmost, efficient allocation of resources and also planning for the deployment of fleets of cargo ships, etc. In 1947, George Dantzig, along with his associates in the US Department of the Air Force, developed the simplex method. Simplex method is an iterative method where the linear programming problem gets solved within finite number of steps. Now, most common applications that you would find for linear programming would be where we are minimizing cost while meeting certain product specifications, maximizing profit with optimal production processes, minimizing cost in transportation routes. So, all the flight scheduling or any other transport problem gets be solved with linear programming. Cheapest combination of foods that will satisfy all nutritional requirements, all of these can be solved by knowing what linear programming is. What is a linear programming problem? Let us take a look at the formal definition and then try to understand the terms involved in this definition. We define linear programming problem as linear programming problem, or sometimes in short read as LPP, is one that is concerned with finding optimal value. Optimal could be maximum or minimum of a linear function of several variables. That function is referred to as the objective function, and this is subject to certain conditions. One of them is that the variables are non-negative and they satisfy a set of linear inequalities which are called linear constraints. Further, when we look at the term variables, they are sometimes called the decision variables and they are always non-negative. So, if I am talking about decision about how many chairs and tables are to be produced, then they are going to be the variables, but of course, since they would always represent certain number, they are always non-negative. So, our decision variables involved are always greater than or equal to 0. Then we are looking at the feasible region. What do we mean by feasible region? The common region determined by all the constraints, including the non-negative constraints of a linear programming problem, is called the feasible region for the problem. The points within and on the boundary of the feasible region represents what we call as feasible solutions of the constraints. Any point outside the feasible solution region is an infeasible solution. Any point in the feasible region that gives the optimal value, that is either maximum or minimum as a requirement of the objective function, is called an optimal solution. So, most of the times our aim would be to find the optimal solution, that is that value of the decision variables, which if I may say call as x and y, for which the objective function takes either maximum or minimum value but is also a point of the feasible region. That is what our task is going to be, and we are going to do this graphically. So, we are going to be using graphs for finding such optimal solution. Let us take a look at first to understand how do we formulate a linear programming problem. What you are going to see in this chapter is that the situation, the entire objective function and the constraints will be stated in words like a word problem, and that has to be converted into linear function, then constraints, and of course, the non-negative restrictions. Starting with, of course, first deciding what are we finding, what are the variables of the problem. And the best way to deal with such an understanding is to take a question and do it. Considering that these statements are going to be rather long, I have chosen problems straight from the NCERT textbook, so that you have a point of reference as well. So, let us start with a problem from NCERT textbook, page 526, and see if we can translate the given conditions into linear programming problem. So, here is the question for all of you, and you can also refer to your textbooks for the same along with me. The problem states, a manufacturer makes two types of toys A and B. 3 machines are needed for the purpose, and the time in minutes required for each toy on the machine is given below. So, it is being described in a tabular form. When you read this table, you can understand that type A toy will need 12 minutes on machine 1 and type B toy will need 6 minutes on machine 1. Similarly, on machine 2, type A toy needs 18 minutes, B does not need any time on that. On third machine, A requires 6 minutes of time and B requires 9 minutes of time. Now, what do we have to find? As per the problem, each machine is available for a maximum of 6 hours per day. If the profit of each toy of type A is rupees 7.50 and that on each toy of type B is rupees 5, find the maximum profit and show that 15 toys of type A and 30 of type B should be manufactured in a day to get maximum profit. Again, dear students, whenever you read a long word problem, the technique that you have been taught is give it one straight reading, then break down the problem into smaller parts and then translate them into algebraic form. Isn't that what you have been doing all these years? So, that is what we are going to do. We will now give another reading to this problem, starting with an understanding of what do we need to find, that is the variables, what is going to be our objective function, what are the constraints given and how do we translate them into linear inequalities. So, when you start reading the question again, you will realize that we have to find the number of types of toys A and B. So, they will become our decision variables. How many type A, how many type B should be manufactured. What else is given is that we need to do this problem with the sole aim of maximizing profit. So, that is how our objective function will be defined. Maximize profit, but how much profit are we going to make depends on knowing how much profit can be made on each toy of type A and each toy of type B. So, on one toy of type A, rupees 7.50. So, if there are x numbers of toys of type A, then the profit is going to be 7.5 times x. To that, we add the profit on each toy of type B, but now I am assuming suppose I have y number of toys of type B, the profit will be 5y. That is how you would be able to get the objective function 7.5x plus 5 times y. Now, what else is given to you? The constraints. Do we work under constraints here? In this case, it is given that the time required for each toy is given in the table, and you are given that the maximum number of hours available for the machine to run is limited to 6. So, that would help us compose the problem. Starting with, of course, as I said, let x be the number of type A toys, y number of type B toys. Objective function, very clear. You have to maximize profit. We generally call the objective function and represent it with capital Z. You may choose to call it P as well. Maximize Z, which is equal to 7.50 times x plus 5y. So, the main thing now that we have to deal with is the constraints. So, for that, if I keep the table in view and I say that each machine can run for 6 hours, but the machine 1 needs to be run for type A toy for 12 minutes. Type B toy, each of them needs 6 minutes on machine 1. So, first thing first is minutes, hours. I have to have the same unit when I am comparing or translating into the inequality. So, number of toys that we have assumed for type A is x. So, if each toy of type A takes 12 minutes in machine 1, then x toys will take 12x minutes. Y number of type B toys will take 6y minutes. And what is the total constraint? 12x plus 6y must be less than or equal to the 6 hours, but instead of 6 hours, we should write 360 minutes. And therefore, the constraints that we get translating for each machine, we will have 12x plus 6y is less than equal to 360. You can simplify the inequality and it will be nothing but 2x plus y less than equal to 60. Constraint on the second machine will give us 18x is less than equal to 360, which gives us x must be less than equal to 20. And the third machine, with the constraints given of how much time each toy needs, it translates to 6x plus 9y less than or equal to 360, simplifies to be 2x plus 3y less than equal to 120. And not to forget, we must have the non-negative restrictions, which is nothing but the number of toys must be always greater than or equal to 0. So, x greater than equal to 0, y greater than equal to 0. This is in totality what we call as the linear programming problem, and this is right now just the problem. Solution will be done in our next lesson. Right now, I am discussing how to formulate the linear programming problem. So, let us take another problem and see how to translate the language into the required LPP. Are you ready for that? Here is our next question, and again, if you have your NCERT book, then let us open that to the page 520 and see what we have to begin with. Let us read this and then translate it into an LPP. The problem states there are two types of fertilizers, F1 and F2. F1 consists of 10% nitrogen and 6% phosphoric acid, and F2 consists of 5% nitrogen and 10% phosphoric acid. After testing the soil conditions, a farmer finds that she needs at least 14 kg of nitrogen and 14 kg of phosphoric acid for her crop. If F1 costs rupees 6 per kg and F2 costs rupees 5 per kg, determine how much of each type of fertilizer should be used so that the nutrient requirements are met at a minimum cost. Also, what is the minimum cost? So, to start with, we are talking about two types of fertilizers, F1 and F2, and what we need to do is find the minimum cost. So, to begin with, our variables will be x and y, x kgs of fertilizer F1, y kgs of fertilizer F2. What else is given to us is the cost. So, if the cost of each fertilizer per kg is given, then the total cost will become 6x plus 5y, and that is the function which we need to minimize. Along with that, there is a condition on how much of nitrogen and how much of phosphoric acid is required. It says at least. So, you need to have minimum of 14 kg of nitrogen. You can have more as well coming from the fertilizers. Each fertilizer has a constraint on how much of nitrogen and how much of phosphoric acid it contains. F1 consists of 10% nitrogen, F2 consists of 5% nitrogen. F1 has 6% phosphoric acid, F2 has 10% phosphoric acid. So, with all of this in view, let us begin with first defining what the variables are, which would be x kgs of type F1 fertilizer, y kg of type F2 fertilizer may be used. Objective function is the cost. To minimize the cost function, say z, which is 6x plus 5y. What are the constraints? Coming back to tabulating the information, which is a best way to understand what is required and given. So, if I tabulate the information, it appears something like this, which is very obvious now, that since I have bought x kgs of F1 fertilizer, the amount of nitrogen that is coming from F1 will be 10% of x, and from F2 the y kg product that I have bought will give me 5% of y, and therefore, 10% of x plus 5% of y must be greater or equal to 14 kg, at least gets converted into greater or equal to, and that is how you would get the constraints, which are nothing but 10 by 100 times x plus 6 by 100 times y is greater than equal to 14, 5 by 100 times x plus 10 by 100 times y is greater or equal to 14. The non-negative restrictions are essential. They would nothing be x greater than equal to 0, y greater than equal to 0. Now, in this problem, I have right now left the constraints looking like as they are, but when we start solving, it would be required that we simplify them. That would help you to plot the graph and deal with the solutions. Now, that is what we are going to do in our next lesson, and therefore, stay tuned and come back to see how we solve the linear programming problems graphically. Till then, all the best.